early, and then when you're a student, for that one semester you have priority. After that, you're back at the end of the line. All right, this morning I'm going to talk to you about what I see coming in seismic hazard analysis in the next 5 years. We are in an exciting time from the point of people doing research in this topic. There are going to be large changes coming. Probably the largest changes that we've had since we added the standard deviation of the ground motion model into seismic hazard in the early 80s. So it's not good for the engineers that want stability, but it's great for us that want to have a chance to make things work and start to see a difference. So the biggest changes are going to come from the ground motion models. And I say that not just because I do ground motion, but this is really where we've probably done the worst job up to this point in sort of going on. So keys that we have to worry about are extrapolation. Almost everything we do in seismic hazard for design ground motions is an extrapolation outside our available data range. And so we do that with combining empirical data and combining analytical modeling from simulations. We can't do this problem simply doing statistical fitting of data. What's really going to be changing is regionalization of ground motion models, and actually a very fine regionalization. So we're going to see, due to the large increases in the amount of data that we've had, we are now realizing how off our models are in particular applications, and we're getting improvements in 3D simulations that support that same move towards a fine regionalization. I don't want to leave out source characterization in my overview here. There are changes to the source characterization, but in the next 5 years, they're not going to move the hazard curves nearly as much as our changes that are really piling up right now in the ground motion model. Part of this is the source characterization models already are source specific. You don't go, if I ask you for the slip rate of a fault, you don't go and say, oh, that fault's 40 kilometers long. Around the world, the average slip rate for a 40-kilometer fault is 2 millimeters a year, therefore it's 2, okay? You would say that's crazy. That's how we do ground motion models right now. So we have a great chance for improving ground motion models. I do think on the source model, moving to inclusion of geodetic data actually really bring that into seismic source characterization will lead to big changes. Every project that I've been involved in that's tried to use geodetic data has gone through the analysis, and at the end we throw it out and say, we don't know what to do. Either the results are really high or the results are really low, and we don't have confidence in the result. But once that gets there, that will start to be a big change. So I think large changes from the source side are going to be more than 5 years away. So when we talk about ground motion models, Christine already mentioned this, so I can say it very briefly. Our traditional approach to making a ground motion model is to group the data from all around the world together based on a similar tectonic framework. So I'd say anything in an active region, anything in a stable continental region, or subduction zones. So we simplify the world into 3 categories and then lump it all together. And we have to have enough data to be able to build a model. Right? So we haven't had enough data at my particular site to build a model that can constrain how things scale at magnitude and short distances. In doing so, we model things like site response by simple parameters, such as the VS30 or the depth of the basin. We model the wave propagation by a simple parameter of distance, and we'll model the source by a simple parameter of magnitude, and sometimes we'll add depth to that. So the cost of that simplification is variability, and that's why we end up with very large variability. Our ground motion parameters, VS30 and distance, for example, are simply proxies that are correlated to the actual physical processes going on. But they're not fundamental physical parameters that describe ground motion. Okay? So that means any model that we build, we're at the mercy of how well our proxy works or is applicable to my particular site. Okay? So VS30 we know is correlated with the deep structure that actually controls the site response. But that's going to depend on the geologic environment. What was the depositional environment at the site? And we expect that to be different for different parts of the world. In fact, not just different parts of the world, but different parts of California, for example. So that means there shouldn't be the same VS30 scaling around the world. But that's what we do in our ergodic models. The same is for distance. It's simply an index for actual wave propagation through the crust. Okay, so we use a term, the linear distance term, which is related to Q, but we therefore, as Q varies around the world, we expect that distance scaling also has to vary. So if we look at it in a very simple way, the easiest way to look at this is on site response. This is just showing you profiles from California and from Japan that both sets have the average velocity in the top 30 meters of about 270 meters per second, but you can see the gradients are really different. So the gradient that actually is going to control amplification will not give us the same values in California or Japan. If we go to a deeper or a higher velocity, you see the same thing. There's a steeper gradient in the Japanese data set on average compared to California. So we can't expect that any model that has VS30 stuck it in as a parameter will work in all of these places. Okay, so each model has to be different. These are examples of what that site amplification is. So the x-axis is the VS30 again, and this shows just Japan and Taiwan and California. These are normalized to about 500 meters per second velocity of 1. So the log of the amplification there is 0. But you see the slopes of those different data sets vary by region, meaning they had different velocity profiles associated with the same VS30 value, leading to different amplification. Part of what happened in the last few years, so as we went from ground motion models in 2008 to ground motion models in 2014 for California, there was some changes in the VS30 scaling. And I was often asked, why did that change? You didn't have a lot more recordings from big earthquakes in California. What happened? So what happened was two things. We did increase our data set, but we also were regionalizing the values. So you can see here the green curve is showing you the scaling in Japan, and the red curve is the scaling in California. And we get different scale factors. So you're going to get different site factors in different parts of the world. And now the next thing we're going to think about, though, is if it's different in California and Japan, is it different from Northern California and Southern California? Or is it different between Los Angeles and San Diego? So we've had a rapid increase in the size of data sets. This is just a plot from the NGA West 2 data set, so it only goes up to just about 2011 in data. The x-axis is the year, and the y-axis is the cumulative number of recordings. So we're getting at every decade about 5 times increase in our data set. If we look at, so right now in 2010 there we had something like 15,000 recordings. If you look at the NGA subduction data set that we're using now, there's 70,000 recordings. So these things are exploding on us rapidly. What this has done is that with these much larger data sets, we can now clearly see significant regional differences. So we knew they were there for years. Christine mentioned I'm trained as a seismologist, and the seismologist would come tell me the ground motion can't be the same in California and Japan. The crust is different, the sources are different, and so forth. And I said, yeah, but it's close enough. Well, it's not. Okay, so that was really, these aren't 10% effects. In fact, we'll see that the dominant piece, or most of the variability we see in our global ground motion models is actually due to systematic and repeatable regional effects. So with this is an example of a data set from Taiwan. And what's shown here is the red stars are earthquake epicenters, and the blue symbols there are recording stations, and every recording station to the earthquake has a green line drawn between it. So if you took all of this data together, we're sampling all of Taiwan. Okay? And so I could get an average ground motion model for Taiwan. But if I just took data here in that area up on the right there, that circled just earthquakes in one region, recorded just at one site, so in the middle here, the site, then I would have the waves propagating only through one part of the crust and recorded at the same site. So now if these earthquakes here tend to be more similar, a similar stress drop on average, the wave propagation has a certain property and the site response has a certain property, I can now explain or remove a lot of that variability. And so we can isolate site effects, and this includes basin effects, path effects, and source effects. And so this is a table many of you have seen before. It's from 2011. For different spectral periods, the ergodic term is the standard deviation we would use if we just lumped all of Taiwan together. The next column is what is the standard deviation of repeatable site effects. This is once I know what happens at that site, how different is one site to another. This isn't random. The sites aren't moving, aren't changing places, right? They have a certain property and it's going to be repeatable. There's a repeatable path effect. This is what happens when we only look at the waves propagating through a similar part of the crust over and over. And the last part is the source. That is, if we look at earthquakes in a small area, do they tend to have, let's say, similar stress drops on average compared to earthquakes in another area? And so when you take all that out, all the things that we can explain that are systematic and repeatable differences, rather than just randomness, we get a remaining non-ergodic standard deviation that's on the right-hand side, and it's around 0.4. So we go from, in this case, numbers near 0.7 down to numbers near 0.4. So that means that about 2/3 of the variance, so the square of the standard deviations, is explainable by systematic effects. So that we have previously treated all that as randomness. And so that's just an incorrect characterization of the problem. So that's what it's just saying. Ergodic standard deviations tend to be 0.65 in most GMPEs, something like that. We remove systematic effects and we get numbers of around 0.4. That value of 0.4 has been very stable around the world. When we do this in California, we do it in Japan, we do this in Taiwan, we get numbers of around 0.4. So that looks to be the limits of what we can explain from systematic effects when we still use this simple proxies for what we're doing, using distance for wave propagation, okay, proxies, and using simple proxies for the source. So now we know how far off our ground motion models have been, right? And it is, as I said, we've been told this for years and years, that this should be different. We now have enough data that we recognize there's a serious problem here. Or a great opportunity to improve our models, and that's what we're trying to do now. So if we look at this as an example, this is the variability of the ground motion from a magnitude 7 earthquake at 10 kilometers and gives for a spectral acceleration of 1 second. And so if I plug that into my GMPE, I get a median of 0.3 G here. And the black curve shows us the range we would use with these standard ergodic models. So I have a broad standard deviation, that's the 0.65 here is used. And what I know, though, is from all that data everywhere that we've looked, when we try to capture systematic effects and remove them, our variability is about 0.4. So I know that the answer is really going to be a narrower distribution. But that narrower distribution isn't still centered on 0.3 G, it's going to be centered somewhere else. And so the issue I need to know is it narrower, but is it higher? Is it near the same average, or is it lower? If you look at what would happen on hazard, here I've done a simple hazard for a single source. I'm going to have only one fault that controls. it makes a big earthquake every 200 years, and I get hazard curves that look like this. I get a magnitude 7 every 200 years. My ergodic curve is the black curve. It has a wider distribution, so it has a flatter slope on the hazard curve. The narrower distributions give me steeper curves, but they shift to the left or to the right. If I was looking at a ground motion value here of even 10 to the minus 4, I could have numbers between 0.3 G and 1.5 G. So you care as engineers about the difference between 0.3 and 1.5 G. Okay, you yell at me when I change the numbers by 20%. So I know a factor of 5 matters. Okay. So this is the potential error that we have by using ergodic models. And so our goal is to now start to try to estimate these numbers so we can figure out where are we, what is the shift for my particular site and particular source, so we can get a much more accurate estimate of the hazard. So there's been a move to non-ergodic ground motion models for about a decade. And now we are ready to charge forward with the implementation. Okay, so in 2008, the NJUS 1 models were sort of here in California, our last great global models. You will not see another set of global models developed by themselves. So average magnitude and distance scaling around the world. Then, as you saw, as those data sets started to really explode in the early 2000s, we started to have enough data, and there were models that could first isolate the side effects. We say, if I have a lot of recordings at my site, I can remove its side effect from the ground motion, and we call those single station sigma models. And a lot of studies were done on that. I didn't list them all, but there's probably 10 studies in that period, all finding the same sort of effect around the world. So then the ground motion models have all are moving to broad regionalization. So NJUS 2 models account for systematic differences in the distance scaling, the large distance term, which we call our linear R term, the VS30 scaling, and the basin depth terms, and a constant term. We also would have that constant term is related, can be related to the source term, like an average stress drop in Japan may be different than the average stress drop in California. The new models that are coming out of the NJ subduction that were discussed yesterday will all have regionalized effects in them. So there will be regionalized models with the same terms, the linear distance term, the VS30 term, and the depth terms being region dependent. Okay. So the question really is, if differences again, if we see differences in broad regions, what's the scale of that regionalization? Do we need to subdivide these into finer and finer regions? So an example of finer regionalization is going on right now in the move towards incorporating basin terms into building codes and into national hazard maps. So that's being done in LA and up in Seattle, and I think in Salt Lake as well, where you have 3D simulations, and you say, how can we incorporate those systematic and repeatable basin effects into the hazard models? Right? That is exactly moving to our non-ergodic models and saying the scale of the regionalization is really over a few kilometers. That's a really big difference than everything around the world is the same. Okay? So this is one of the CyberShake calculations. This is an old one, CyberShake 1, but the idea here is the scale of this regionalization. One of these sizes here is about 25 kilometers, so you can see you have regional differences on the scale of a few kilometers that you can see in this area, right? So that's really what we're heading for. So how do we do this? So if you're going to start to add these systematic regional effects, so 3 things you need to do. You need to estimate the term. Okay, so you can, for example, basin effects, you can be running your 3D simulations to estimate it. You need to reduce the aleatory variability. If you put those terms in, that standard deviation needs to come down. Okay? And then the third thing you need is you have to get the uncertainty in your ability to estimate that term. Okay, so we're going back to these pictures here. We need to know how much did this shrink, where is it centered, and what is my uncertainty in where it is centered. Okay, what the value is. So right now, if we're adding basin terms, that's happening currently is to take a hazard curve. For example, this black curve. Sorry, this is the ergodic ground motion model curve, the standard way we run it. And then in this case, let's say we have a site that says the basin factor is 1.5 times what it is in the GMPE. So we should have more basin amplification. I'm going to scale it by 1.5. So we simply scale the x-axis here by a factor of 1.5 and move it to the right. And though they use the same slope of the hazard curve, there's been no reduction in the aleatory variability. So that's easy to do, but it's missing two important pieces of the problem. So this is not the way to incorporate non-ergodic effects into your models in a way that is going to be have a framework that can move forward and be consistent over time. So what we want to do instead, here is the same example. I'm going to say I have that same factor of 1.5, and this reduces my aleatory variability from 0.72 to 0.6. Okay, that's sort of at long periods what we're looking at. And then here we're going to say my epistemic uncertainty in the basin terms I've just assumed is 0.2 natural log units. So that means you know pretty well what you think that basin term is. So you have some confidence in your modeling. So in doing that, we're now going to get 3 hazard curves that are steeper. Okay, so the black curve is identical to what I showed you. The curves are shifted to the right. The center one there, the red curve is shifted by a factor of 1.5. The other one is shifted by a factor of 2. The one is shifted by a factor of 1.1. So that's using 1.6 times the standard deviation. And then we get a mean hazard curve that is is very similar to the median, but shifted as we go further over, it's starting to be pulled up because it's the mean of these curves. Okay, that's the curve that we want to be using. We don't want to just be using a shifted model over. This makes the most difference when you're at a high number of epsilons, right, or a high rate of earthquakes, so that you're having to go out on the tail of the distribution to control the answer. If you're in areas of low activity and you're at median ground motions, then this is not a big issue. If you're outside the basin, so now what do? You go outside of the area that you modeled. How do you merge those two things? How do you shove your basin model on top of the rest of the model? And the way to do that is the same way running the non-ergodic model here. So here, though, we're going to say the basin term on average is going to be 1. Excuse me. Meaning I don't have information there, so I'm going to say it's centered on my average model. I'm still going to reduce the aleatory variability from 0.72 to 0.6. Not having information on the basin response doesn't magically change the aleatory variability. It has its own value, and that's what it is. So we actually know those terms pretty well. What I don't know is where it's centered. So I now put in a large epistemic uncertainty, an epistemic uncertainty that represents no knowledge of the basin term. And then I just look at how does that vary across random sites. So in doing so, my curves now, the black curve is my ergodic one. The red is that same factor of 1, but with a steeper curve. And then the blue is a low factor, and the green is a higher factor. So those are my epistemic uncertainties. The dashed line, the mean, you can barely see, is right on top of the ergodic mean. So if we don't have any information and we separate this back into, we do the analysis and separate the epistemic uncertainty and have our non-ergodic model with smaller standard deviations, the mean hazard comes out basically the same number. So that's good. That means we have a way that we can smoothly vary from having data where we're adjusting the model to, as we go to lessen data, it just smoothly goes back to the ergodic mean. But we also know that there's uncertainties. And those uncertainties would have been lost if I hadn't been able to show you what this range is. So hazard maps with 3D basin effects, we should be running these partially non-ergodic models. Okay, we use the basin terms with epistemic uncertainty in regions where we have those estimates. In regions without it, we use the median with no term, so a unity on the scale factor, and includes the large epistemic uncertainty. And we get a smooth transition. So this is the way that you can have a framework that can accept pieces of information as it comes in, and you can update the model. If you go now to San Jose and say, I want to add that, you can drop it into the model and have it smoothly go out and sort of merge with the parts of the model that don't have the 3D modeling. And so it's just a framework I think that's going to be much better. So what's next? We have moved to non-ergodic models. Okay, you may not know it, but that's already happened. So we have regionalized our broad regionalization is in the ground motion models. We are starting to add specific basin terms. What's the next thing that's coming? And the next thing is continuous spatial regionalization. So if you think about the way we do smooth seismicity and hazard models, right, instead of drawing a zone and saying it's uniform seismicity there, we can have smooth seismicity that mimics the distribution of earthquakes. But we can do the same zoneless model for our ground motion model. So we don't have to draw a region and say this region has one GMPE, this region has another. In doing so, we have the coefficients of the GMPE vary as a function of the location of the site and the source. Okay. The next thing, and so those models exist right now. We're just starting to try them out. The next thing that we're doing though is looking up. Let me step back. So those have isotropic path effects. In other words, the ground motion attenuation at my site is the same in all directions. Okay. And the other way we can look at this is to actually have source and site-specific path effects in our ground motion model. And so we allow the distance scaling to vary depending on where the source and site are located in the particular ray path that they're taking. And so now we're beginning to mimic what the 3D modeling is doing. Okay, it's a crude way of doing it, but we're sort of slowly moving in that way. So I will show you a couple equations, but they're really easy. Okay? So all I want you to do is, because it's easiest for me to show you this, and pay attention to the red terms. So our ground motion model, if you've seen them, there's some function of magnitude, there's some geometrical spreading, times the square root of the distance, or log of the distance, excuse me. There's a linear distance term, and then some terms of style faulting and depth, and there's a term with VS30, and there's a term with hanging wall, and there's a term with nonlinear site response. Forget all that stuff and just focus on the ones that are red. Those are the terms that we are now making regionally dependent. Okay? And in this spatially varying model, those terms are going to vary as a function of just the coordinates of your site and the coordinates of the earthquake. So in doing so, we make our new non-ergodic model, where the GMPE is the old standard model that we've got published, at the top, the same one, and now we're just going to say, how do those coefficients, this delta, deviate from zero? And they're a function of the location of the earthquake, or the location of the site, or in some cases, the location of both of the earthquake and the site. And so when we start to do this for the distance term, the linear scaling, we're going to grid up California into, in this case, 30-kilometer grids. And we're going to calculate from my site to the earthquake the distance within each grid. And that starts to become, going back here, those delta R's in the bottom. The distance within each grid times an adjustment factor times the grid. So we're doing really crude tomography, is the way to do it. We don't do it with tomography. We use little different ways of doing this with statistical methods that we basically put a prior on what the range is of these numbers and do Bayesian regression, but that's just a statistical way to get smooth values, and when we're in areas with no data, it goes back to a default of 0, okay, but with large epistemic uncertainty. If you look at what this does, on the left-hand side is a map of the peak acceleration. It's in natural log units. Just think of the light colors, the yellow as being high values, the dark colors being low, and there's about a factor of 10 from the high to the low across the country, or across California. So trying to predict the magnitude 6 at 10 kilometers, the median can vary by a factor of 10 in different parts of the state. On the right-hand side is the uncertainty, the epistemic uncertainty in that value. The darker colors are low uncertainty, meaning I have data to constrain the model. Up in northeastern California, where I have very little ground motion data, my model defaults back to an average, the global or the regular GMPE we've been using, but I have a large epistemic uncertainty associated with that, shown by the light colors on the right-hand side. So again, we have a smooth way of transitioning between where we have data and where we don't. I'll just show you briefly what these coefficients look like and their scale. If you're looking at on the left-hand side is the VS30 scaling term. So that has pretty broad correlation lengths to it. They may be on the order of 50 kilometers or more. On the on the right-hand side is geometrical spreading term, so that's times the log of the distance. And you can see the Bay Area is lower geometrical spreading, and the LA region is higher geometrical spreading. That's changing the slopes of the GMPEs. Again, here now the scale is correlation lengths are more on the order of 15 or 20 kilometers. The left-hand side here shows the site term. The site terms, you need to be really close to your site to get anything out of it. So these are kind of bullseyes around where the stations are. Okay, and so most of it is zero, meaning you need to go do a site response. We're not going to get at site terms from empirical studies like this. On the right-hand side is the source term. So our sources in Northern California are a little larger than they are down in Southern California, and that's counteracted a bit by some of the changes in the distance scaling. Then we get the uncertainty. What is our uncertainty in that estimate? Okay, and so this is that same map that we've shown. So this is going to tell us where we have data to constrain these models. I have lighter colors, so around the Bay Area and around LA where we put our stations. And areas without it where it's poor coverage, I have large uncertainty. The other part we have is that attenuation by cell, and this just shows you what we can estimate. So most of California defaults to zero because we don't have the data to get at it. The cells that have colors in here are ones where there's enough data now to estimate what is the attenuation through those. And then we have the uncertainty in those. So the left-hand side there just shows you how many rays pass through each cell when I do each combination of earthquake source and site, and the right-hand side is the standard deviation of those. So again, where the data are, we have smaller sigmas. Where the data are not, we have big epistemic uncertainties. So when we do this, going forward, we've been talking still about the non-ergodic parts of the ground motion model. But for seismic hazard, we again are driven by extrapolation of these models. So we need to still keep track of what is our uncertainty in the extrapolation. So we have to have that in our base scaling models. What we're talking about now for the non-ergodic is a deviation that goes on top of this uncertainty in the extrapolation. Right? So both of those things are there. So when we start to do this, I'll show you an example of hazard calculations that are done with these kinds of models. For the source characterization, I'm going to use the standard models that we use, have standard epistemic uncertainties in them. And then the base models have the alternative magnitude scaling, alternative distance scaling, and then we have the alternative non-ergodic models for those spatially varying coefficients. So we have a median and a standard deviation of each of those. And to sample them, we need to take about 100 samples of them. So that's a lot. If you run hazard and I tell you you run 100 GMPEs, you're going to get mad, right? And say, I'm not running 100 GMPEs. And the USGS say, we can't possibly do that. But we have a solution to that one as well coming. But you need that to be able to capture the uncertainty range. So let me show you quickly some examples here. This is a site in San Jose. So they're shown by the circle. We have data in San Jose. We have pretty good source characterization data there. And we have ground motion data. On the right are hazard curves. And the black curves are from the ergodic model. And the red curves is the uncertainty from the non-ergodic model. And you can see they're getting steeper hazard curves, meaning we knew the aleatoric variability is less. And I had enough data to constrain the model, so we can constrain those non-ergodic terms. If we go to northeastern California, there's no data up there to constrain the models, so I have very large epistemic uncertainty in my non-ergodic terms. It's still there. Northern California doesn't suddenly behave like an ergodic region. Okay? No data means large uncertainty. It doesn't mean large aleatory variability. Okay, so going here, we see that black curves have a range, let's say about a factor of 5 in the y direction, or a factor of about 2 in the x direction, whereas the red curves are showing you the broader uncertainty range that we get when we put in the non-ergodic models. And so now we're getting closer to factors of 5, and what the ground motion hazard could be at a given, the ground motion could be at a given hazard level. The means are the same. Just like I showed you for that very simple case, the mean hazard becomes the same. All I've done is shifted aleatory to epistemic uncertainties, but the medians are shifted down. More sites, more than half of the sites, the hazard will be lower than what we had from our ergodic mean. For some sites, they'll be higher. Right? That's the way it's going to work. This is a site near San Luis Obispo, and in this particular case here, we have not much ground motion data, but pretty good source characterization, but there's some ground motion data here. You can see the hazard curves becoming steeper still. The red curves are steeper than the black. However, they're shifted to the right. So in some places, and this is a case where the hazard goes up due to the non-ergodic models, meaning they have shifted, the GMPs have shifted to higher ground motions on average, but we know the variability is less. So we can use these things. This is an example as well. If you were looking along the Hayward fault at sites that were all 2 kilometers away, if we ran our ergodic model for the same site condition, we get the same ground motion. Right? Plug in 2 kilometers, that's what you get. Our non-ergodic model, this red curve shows you the variability we get in the median when we start to put in our non-ergodic models. So we're starting to get at the kinds of effects that the 3D simulations are also trying to get at. Okay. So constraining these terms. So do we have enough data to do this? Is this just craziness, right? We can't possibly do this. We need so much data. And the answer is yes, because we have some data. And the framework of the model allows for a smooth transition, and it takes data as it comes in, and the model smoothly adjusts itself. In areas without data, we get back the same mean number as the ergodic hazard, but larger uncertainties, which is what should be there. No data means larger uncertainties in the models. Okay? We do have to start to supplement our empirical records with 3D simulations. We're not going to get there solely based on waiting for earthquakes to happen. Okay? This, though, needs adequate validation of the 3D simulations. And the current efforts at adding basin effects into seismic hazard are supplementing empirical data with 3D simulations. That's exactly what they're doing. Okay. How would we start to use this? So one more equation. Don't pay much attention except to the left-hand side. We do 3D simulations, and we need to normalize them by something. We have to make them match with the GMPEs. Centering simulations on the GMPEs is a big issue for us. So that was discussed yesterday on directivity. How do you make that work? It's the same thing here. So we normalize them by a 1D simulation, but it is not the 1D model for the region. This is the 1D velocity model that goes with the GMPE. And it is not a realistic model, because the GMPE is averaging a whole bunch of different velocity models. But we want the model so that when you put it in there, we're correctly centering your simulations on the GMPE. So what we're seeing is we're going to be mixing empirical models and simulations. But we've been doing this for years. Good GMPEs are not statistical fits to data. We call them empirical, but that's not what they are. Okay? We use simulations to constrain how those models extrapolate. Physics-based simulations are not purely physics. They have to calibrate themselves or validate themselves against the same empirical data that we use in our empirical models. You have to check that they're working. There are parameters in all those models that are optimized or adjusted to fit observations. So there's a tremendous overlap between these methods already, and all we're doing now is talking about more overlap. To make this better, we're going to be moving to Fourier amplitude spectra. So if you haven't seen that, that's coming. As engineers, you don't need to worry about it yet, but start to pay attention to Fourier spectra. The main reason we want to do this is it is a much better way to tie the physics of the seismology to the empirical models. Using response spectra is just a screwy parameter that has all sorts of very bad behaviors that aren't clear physically. So we are going to be building FAS models, and that's happening right now. So why don't we just use the 3D simulations and be done with it, right? That's what CyberShape does, isn't it ready to go? And the answer is no. Okay, so from my side and someone who needs to apply these, I have to have an epistemic uncertainty in the extrapolation of the models, in the base modeling. You would have to run a whole series of different models of the source generation to be able to start to get there for me and show me that you're capturing that range of epistemic uncertainty. The other part is we haven't got to adequate validation for use on engineering projects of the 3D simulations. We've done it on the 1D for medians. We still need to deal with the variability terms and the 3D models. So as we go to this non-ergodic framework, I want to use this framework to take 3D simulations and integrate them into our empirical models. So it allows us to be done in a way that fits with the GMPEs. The spatially varying coefficient approach is really nice for us because it doesn't have to draw boundaries. We don't have to figure out what happens when the earthquake's in one vent source and the sites in another source. And again, we have a nice smooth transition from regions with data to regions without data. So we're heading to a phased approach on how we're going to do this. The first phase is where we are now, is running ergodic, non-ergodic GMPs with epistemic uncertainty as a baseline. Our next part here is we're taking the 3D simulations for the medians only right now and using them to update these non-ergodic terms so that we can start to integrate them together. But we're going to run hazard with the empirical aleatory variability. Third phase, which is a few years down the line, once we get the variability validated for the simulations, then you can use the simulations for both the median and the variability. So when we start to do this, again, you're not going to be happy about running 100 branches of GMPs in your hazard, but we've got an alternative approach, and so there's work going on right now to develop analytical methods to propagate the epistemic uncertainty in the hazard. So you just run it for the median, the center model once, and we do all the epistemic uncertainty in a very quick analytical calculation outside. It's an approximation, but it's a good one, and this ought to be ready running next year. So that should solve our numerical problems. So we know how far off our ground motion models are, and we're going to have new ground GMPEs will continue to add more and more region-dependent terms. That's inevitable for us. They're going to get more complicated. This means numbers are going to change. As we start to make things more region-specific, the values aren't going to be the same as they were when we used an average for the whole world. Okay? So an example, 2,500-year ground motions could go up or down by a factor of 2. That's just what's going to happen as we start to recognize systematic effects and try to get more accurate calculations of our hazard going forward. Thank you.